Section 2.5 is going to be measures of position for a data set. So the measures of position, what that means is that it chops the data into sections when the data is in order. So we'll start with quartiles. So there's going to be 3 quartiles, and what these quartiles are going to do, which the name suggests, it's going to split or divide the data into 4 equal parts. So let's pretend like our data is in a straight line here. And we have this value all the way at the end. This is going to be the minimum data entry, so the smallest data entry. The data entry all the way here at this end would be the maximum, so just the largest because they're in order. And we know that the middle piece right here would be the median, right? We're going to call this the second quartile though. So I'm going to put Q2. If we chop up that first half of data, we would have another quartile right here. This would be the first quartile. Same thing if we did it for that second half of data, chop that in half, and then we'd have the third quartile. So these equal parts of 4 that we got are going to be approximately 25% of the data. So between the smallest, the minimum entry, and the first quartile, about 25% of the data will be there. Between Q1 and Q2, another 25%. Between Q2 and Q3, another 25%. And between Q3 and the maximum value, another 25%. And I just wrote down real quick that what all the Qs, Q1, Q2, and Q3 represent. And just a little note down here. The second quartile is the median, which I mentioned, but that's very important because it's going to help us find these quartiles. Okay, so let's actually do an example here. So let's find the first, second, and third quartile for the following data sets. So the data has to be in order. So the first, it looks like the data is already in order. So the first step, the first thing we have to do is find the second quartile first. So we find Q2 first, and the reason that we do this is because it's the median. So when we're finding this, do it however you like to do it, whether it's crossing off values. The middle value here is going to end up being, I believe it's 16. Okay, so that means Q2, write this down a little bit lower because I'm going to need room. Q2 is going to be 16, so that's the second quartile. For the next step, we need to chop the data into 2 equal halves based on the median. The first quartile, Q1, is the median of the first half of data. So we know that the median, the actual median, Q2, chops the data up into 2 equal parts. So that's going to be this first part right here. So Q1 is going to be the median for that first part. So we find the median within those parentheses. That's going to be 9. So Q1 is 9. And the last thing is Q3. Q3 is going to be the median of the second half of data. So we're going to do what we just did, except do it to the second half. So parentheses around the second half of data. Find the median. It looks like that's going to be 33. So that is going to be Q3. The third quartile is 33. Okay, so we would say about 25% of the data is between the minimum value of 6 to Q1 of 9, another 25% between Q1 of 9 and Q2 of 16, and so on. So let's do one more of these ones. So we have the small data set, 11, 8, 15, 6, 12, and 8. So we can see here that the data is not in order. So we have to put it in order. So putting this data in order, it's going to be 6, 8, 8, 11, 12, 15. Okay, so now we can do exactly what we just did. So we're going to find Q2 first. So Q2 is just going to be the median once again. So finding the median here, it looks like it's going to be between 8 and 11 because we have an even number of data entries. So the median is going to be the average of those two numbers. So we have to add them, divide by 2. That's going to be 19 over 2, which is 9.5. So that is going to be our Q2. Now we have to find the median of that first half of data, which is going to be Q1. So the median here is going to be 8. So that's our first quartile. And the median for the second half of data is going to be 12, which is our third quartile, so Q3. So there's Q1, Q2, and Q3. And then for the next thing is the interquartile range. So we're going to abbreviate interquartile range as IQR. The interquartile range is IQR equals Q3 minus Q1. So just like the range of a data set, it's the max entry minus the minimum entry. This is essentially the range of the quartiles, hence the name interquartile range. So we just subtract Q3 minus Q1. And using how the quartiles chop up the data, the IQR is going to span about half of the data, 50% of the data. So we're actually going to use this to help us find the outliers. So it's probably pretty obvious what an outlier is. It's a data entry that we consider far away from the other data entries. So the way that we actually define what far away is based on this interquartile range. So the way that we do this is we find Q1 and Q3. We use that to find the interquartile range. And then we have to calculate Q1 minus 1.5 times the interquartile range. So make sure your order of operations are correct and you do the multiplication first. So any data entry that is less than that value is going to be an outlier. And then we're also going to calculate Q3 plus 1.5 times the interquartile range. Any data entry more than that value is going to be an outlier. So let's see this with an example. So find any outliers in that data set. So it looks like it's already in order, so that's cool. So finding, we actually already did this one. This was a previous data set. We found that Q1 was 9. If you wanted to retry it again, go for it. Q1 was 9, Q2 was 16, and Q3 was 33. So calculating the IQR, that's going to be Q3 minus Q1. So 33 minus 9 is 24. So the interquartile range is 24. And we're going to use that to find the outliers. So it's going to be based on right up here. It's going to be Q1 minus 1.5 times the IQR. So this is going to be 9 minus 1.5 times 24. This is going to be 9 minus 36. 1.5 times 24 is 36. And this gives us negative 27. And the next one is Q3 plus 1.5 times the IQR. So it's going to be 33 plus 1.5 times 24. Oops. So it's going to be 33 plus 36, which gives us 69. Okay, so what this means is that any value less than negative 27 or greater than 69 in the data set is going to be an outlier. So we go up to the data set and we look for values less than negative 27, which clearly there are not any, and values greater than 69. we do have a value greater than 69. That's going to be 104, which is probably obvious if you just go back and look at the data set that seems like it's going to be an outlier. So this means that 104 is an outlier. It's our only outlier. All right, for the next thing here, it's the 5-number summary. So the 5-number summary is referring to the numbers, the minimum value, Q1, Q2, Q3, and the maximum value. So those are going to be the summary here for the 5 numbers. So we're going to use this 5-number summary to create a little graph. It's going to be what we call a box and whisker plot. It's just going to be a little bit of just another way to visually represent the 5-number summary here. So this is what it looks like. So it's called a box and whisker because we obviously have this box right here. And then these values down here, or these lines, would be the whiskers. So the 5 numbers here, the minimum value is going to be all the way over here on the left. Q1 is going to be the leftmost part of the box. Q2, the median, is going to be the center line in the box. Q3 is the rightmost line in the box, and the max value is all the way over here at the endpoint. So doing an example with this, let's create a box and whisker plot above this number line down here for this data set. So this is actually the data set, once again, that we've already done twice in this section, just so we don't have to go through and do every calculation again. So it's already in order, and it's pretty easy once it's already in order. The minimum value here is 6. So we need Q1, Q2, Q3, and the max. The maximum value is 104. Q2 is 16. It's the median. We chopped the data up and we said Q1 was 9 and Q3 was 33. So that's all we need. Those are our 5 numbers for the summary here. So let's create this box and whisker plot. So finding the minimum value is 6. So 1, 2, 3, 4, about right here. So we're about here. And the maximum value 104 is going to be about right here. Q1 of 9 is going to be right here. Q2 of 16 is right over here. And Q3, 33, right here. So we're just going to create this box in here. And the whiskers, just connect that to the box. So this kind of helps us visualize that outlier of 104, that is most likely an outlier because that whisker is so long. Okay, so that's the box and whisker plot. So let's do about one more of these ones to make sure that we're good with it. So we have this data set. So this is actually not in order. So we have to put the data in order. So it looks like it's going to be 2, 6, 7, 8, 8, 9. So 2, 6, 7, 8, 8, 9, 10, 10, 12, 16. Okay, so we need our 5 number summary. We need our minimum. We need Q1. We need Q2. We need Q3. And we need the maximum value. And the number line's not on the page, but it's down below that we'll put it on the box and whisker plot. So finding the minimum, obviously the minimum is just right here, is 2. The maximum is 16. So finding finding Q2, the median, it looks like the median is going to be 2, 3, 4, 5. It looks like it's going to be between 8 and 9. So the median is going to be 8 plus 9 divided by 2, so it's going to be 8.5. So that's our Q2. So now when we're chopping up this data, it's going to look like this and this on the right side. The median of the first half is going to be 7, which means that's our first quartile. The median of the second half is going to be 10, so that's our third quartile. And there is our 5-number summary, so pretty simple. So we're going to use that to create a box and whisker plot. So the minimum of 2 right here. Q1 is 7, so right here. Q2, 8.5. Q3 is 10. And the max is 16. So we have a box. And connect your whiskers, and that is our box and whisker plot. So this one actually looks kind of decently symmetric compared to the other one. Okay, so that's it for that portion. For the next thing, so far what we've done was quartiles. Quartiles are a way that we chop up the data. That belongs to a bigger idea called fractiles. So another fractile is the percentile. So a quartile divides the data into 4 equal parts, and there's 3 of them. Percentiles divide the data into 100 equal parts. So percent, so 100, like 100%. And there's 99 percentiles. So we use percentiles when we're trying to compare one data entry to the whole group to see what percentage it's bigger than. So for example, like a percentile for your class ranking, if you were at the 87th percentile, then your grade, your GPA would be better than 87% of everybody else. So kind of just like I mentioned, the percentile of a data entry represents approximately the percentage of data that falls below it. So the little formula for this is going to be the percentile of a data entry X is going to be the number of data entries less than X. We just have to count how many are less than X, divided by the total number of data entries, and then we have to multiply it by 100 to get a percent. Okay, and then I put a little note, we have to round to the nearest whole number. So let's do an example. So we have this data set. So we're going to use it to find the percentiles for each one of these examples. So first one is 11. So we have to find 11 in the data set. So here's 11. So the percentile of 11 is going to equal the number of data entries less than 11. There are 1, 2, 3, 4, 5 data entries less than 11. Divided by the total number of data entries, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 data entries. So 5 divided by 9 times 100. Plug that in your calculator, you get about 55.6%. So I'll leave the percent out for now just because I didn't have it on the 100. So 55.6. So this is going to round up to 56. So round to a whole number. So the percentile of, oops, I forgot to put 11 here. Percentile of 11, we would say 11 is at the 56th percentile. So 56th percentile. And that means that data entry of 11 is going to be greater than about 56% of the data, which if you look back up at the data, it looks like that's about true. It looks like it's greater than just over half of the data. Okay, for the next one, for 5, so the data entry of 5 is right here. So we want to find the percentile of 5. So it's going to be the number of data entries less than 5, so we have to count. So 1, 2, there's 2 data entries less than 5, there's 9 total. So 2 divided by 9, multiply that by 100, and that is going to give us 22.2. So we have to round, we get 22. So that means 5 is at the 22nd percentile. which once again means that the data entry of 5 is greater than approximately 22% of the data. Okay, so for the last one here, we have 19. So I put this one in here on purpose because this isn't the only way, technically, that you can calculate percentiles. There's a little bit different of a way to do it. And this one will show you kind of why there's a different way to do it. So the percentile of 19, you can see that 19 is the last data entry, right? It's the largest one. So you may think that it's at the 100th percentile or the 99th percentile, but the way that this calculation is set up will make it not that way. So we'd count how many are below it. 1, 2, 3, 4, 5, 6, 7, 8. So 8 below that data entry divided by 9 total times 100. This is actually going to give us 88.9, which would be about 89. So this means that this data entry 19 is at the 89th percentile. So it's a little weird just because this is saying that 19 is greater than 89% of the data, but clearly it's greater than all of the data because it's the largest data entry. So that's why this one's a little bit weird, but based off this way to calculate it, that's what this answer would be for it. Okay, so kind of switching gears just a little bit. So that's it for that little section. So switching gears for this last page for the standard score. For this one, we are going to also measure the position of a data entry. So far this whole section we've been measuring position. Now we're going to do it with the mean and the median, or the mean and the standard deviation. So before we were doing it essentially with just the median, calculating the median for Q2, the median of the first half is Q1, median of the second half, Q3. Now we're going to be measuring the position using the mean and standard deviation. So this is called the standardized score, which is the Z-score. So this is going to be coming up a lot more in later chapters, but we're just going to touch on it for right now. The Z-score represents the number of standard deviations a data entry X is away from the mean. So that's very important so we know what it actually means. So the formula for this is Z equals the data entry or the data value, whatever it is, minus the mean divided by the standard deviation. So if we were to write this in symbols, which we will be writing it in symbols, it's Z equals X, X is the data entry, minus mu, population mean, over sigma, which is the standard deviation for the population. And a Z-score can be positive, negative, or 0. If a Z-score is positive, that means the data entry is greater than the mean. So that means it would be that many standard deviations to the right of the mean, meaning it's greater than. If it's negative, that means the data entry is less than the mean. And if it's 0, that means the data entry would be just equal to the mean, because that would give us 0 in the numerator. So let's do one last example here for this. So let's say the mean of vehicles on a highway is 56 miles per hour. So I'm just going to write that down, kind of write down our givens as we go. So the mean is 56 with a standard deviation of 4. So mu 56, sigma 4. And then we find the measures of, we find the speeds of 3 cars, 62, 47, and 56 miles per hour. So we want to find the Z-score for each one of these speeds. So let's start with the Z-score for X equals 62 miles per hour. So it's going to be z equals x minus mu over sigma. So it's pretty much plug and chug. So x is 62 for this one. 62 minus the mean is 56 over 4. So calculating this, just make sure if you're throwing it in the calculator all at once, you have parentheses around that whole numerator. So 62 minus 56 is 6. 6 divided by 4 is 1.5. So z equals 1.5. So what this means is that 62, the data entry of 62, is 1.5 standard deviations above the mean. Okay, we know it was above the mean because it was positive. So the next one here, let's do 47. So we're going to find the z-score for the x value of 47. So same formula, z equals x minus mu over sigma. Plug everything in, x is 47. Mu is 56, the mean, over standard deviation of 4. So this is going to give us 9 over 4, which will be negative 9 over 4. So it's going to be negative 2.25. And then what this means is that 47, the data entry of 47, is 2.25 standard deviations below the mean. And we know it's below the mean because it was negative. And for that last one, it was 56. So before even calculating it, you should recognize that this is the same as the mean. So based on what was written at the top of this page, you should already know what's going to happen here. So calculating this z-score, we get x minus mu over sigma. So it's going to be 56 minus 56 over 4. 56 minus 56 is 0, so the whole thing is just 0. Okay, so what this means is 56 is 0 standard deviations away from the mean. And then what this obviously means is 56 is the mean. So this data entry just so happened to be equal to the mean. Okay, so we'll be coming back to that in chapter 5 or whatever it is. So yeah, this section is measures of position. So we focused on quartiles, did a little bit of percentiles. That was using the median. And then we also found these measures of position using the mean and standard deviation. Okay, so that's it for 2.5.